Welcome everyone to DuQIS speaker series featuring Dr. Mark Jackson from Cambridge Quantum Computing. And it's a great honor to have him here. So I'm going to give a little introduction to Dr. Mark Jackson. So Dr. Mark Jackson is a scientific lead at Cambridge Quantum Computing. He received his Bachelor of Science in Physics and Mathematics from Duke. And after that, he went to Columbia University for a PhD in theoretical physics. And he then spent 10 years researching superstring theory and cosmology and co-authoring almost 40 technical papers. And he's really interested in promoting understanding of science to the public. So he founded the science crowdfunding platform Via Physica, a nonprofit science partnership fund. He is an adjunct faculty at Singularity University and a director of Astronomers Without Borders. So please join me in welcoming Dr. Mark Jackson.
Thank you, Catherine, and thank you, Ken, for hosting me. It's really a special pleasure for me to be talking with you today. As Catherine said, I was an undergrad at Duke, and I majored in physics and math, and I would love to be joining you in person. I would love an excuse to come back to campus and visit. I've only been back once in 21 years since I graduated, but unfortunately circumstances don't allow that. And so I'll have to do this for now, but I hope that maybe in the spring I could come back and give maybe a more personal talk of what I've been up to for the past 21 years. So I worked for Ronan Plesser back then, who I think some of you might know, and then I went on to do my PhD at Columbia with Brian Greene, who Ronan introduced me to. And so I did do string theory for many years, and then about 6 years ago, I kind of decided to do something else, and I briefly did this Fiat Physica science crowdfunding website, and then I briefly returned to academia before joining Cambridge Quantum. And to give you a little bit of background on that, here, let me actually put up my slides here. There, can you all see that there? It's great. Yeah, so I was living in Berkeley, California, not because of the university. I just happened to be living in Berkeley when CQC hired me, and we were introduced through a mutual friend, Ed Frankel. Some of you might know he's a math professor at Berkeley. And so he introduced me to the CEO, Ilyas Khan of Cambridge Quantum. And I'd been wanting to get into quantum computing for a few years. This wasn't really a field, at least not in a major sense, when I was studying. I wasn't even really aware that quantum computing was being researched when I was an undergrad. And so because I've been hearing about all the developments and it seemed so exciting, and it seemed such a good combination of both physics and computers, and it seemed to be kind of capturing the public imagination of what this could mean. And there were enormous business opportunities, of course. And so I'd been wanting to get into it for some time, and I didn't know how to do it. It's tough to break into a field when you don't know anyone and you don't have a background in it. And so I kind of was asking everyone I knew, like friends and friends of friends and so forth. And so I was having dinner with Ed Frankel one night, and he said that he knew 2 people in the field. And so he made these 2 introductions, and one of them was to Ilyas Khan, our founder and CEO. And within a few months, I was working there. And so I was the first US employee. Let me tell you a little bit about the company. So we're about 6 years old. We were started in 2014. And funny enough, this makes us one of the oldest quantum computing startups. And we were started because Ilyas is chairman of the Stephen Hawking Foundation. And 6 years ago, Hawking told him, quantum computing is going to be big. You should get into this business. And so we have kind of a great origin story that Stephen Hawking is responsible for starting our company. And it did come out of the University of Cambridge. Our first scientists were at the university, and our official headquarters is still there. So it's actually the compiler team and the chemistry team are in the Student Union building at Cambridge, if you know where that is, behind the round church. Our business team and our machine learning team are in London. And then there's about 6 of us in the US. We're all on the business side. And we also have 3 people in Japan. There we go. So we've now grown to about 120 people, which also makes us one of the largest quantum computing companies now, about 2/3 of whom are scientists, many with PhDs. And then there's assorted people on the administrative and business side. And funny enough, even though I do obviously have a physics background, I'm on the business side of things. And I'm mentioning this because I want to impart to you that even if you don't end up actually doing the science on something, it's good to have a scientific background. Even in the business world, I kind of act as the liaison between the business and the scientists. So I'm usually the first one talking to customers, explaining what we can do and what quantum computing is, and I have to explain this to our scientists. I'm usually the one presenting at conferences, and so it gives me a lot of credibility that I can understand at a technical level what we're doing, even if I'm not the one in the lab actually doing the research. And this is a field where you can't just be a salesperson kind of with a sales background. You actually, our CEO likes to joke that even our salespeople have PhDs in physics, and that's true. And so so there's a lot of opportunities, and it's really great that you're getting into this. So I would encourage you to learn as much as you can technically, even if you don't end up being an actual researcher. So we have partnerships with IBM and Honeywell and Google and Microsoft and others. So we're focused primarily on the software. We're not actually building the quantum computers, but we have these partnerships because we want to use them. And so we have access to all these machines. We're in their official developer partner networks. We have especially close relationships with IBM and Honeywell. They've actually invested in us. And so these are minor investments. We're very careful to stay neutral for all of these platforms. We work with all of them. But IBM and Honeywell have actually authorized us to resell access, and I'll talk about that later on. So what do we do in the company? So we have 4 focus areas. So the first is, it's a compiler that we call tket. I'm sure all the physicists in the audience, you understand the pun there. So the T was from our original CTO's name, and then the ket is obviously from physics, and so we call it tket. And so this is a quantum compiler, and I'll be talking a lot more about that later on. We have a chemistry application, which we call Human, and we've already been developing this with a lot of commercial partners. We have a machine learning program, both like kind of normal mainstream machine learning, and we have a special focus in natural language processing with Bob Cook at Oxford. And then finally, we have a division focused on cybersecurity. So we've developed a way to produce random numbers in a way that you can prove that they're random. And this is done using the Bell inequality. If anyone, I'm not going to focus on that in this talk, but if anyone has any questions later on, I personally find this amazing, because if you had asked me just a few years ago whether there would be a commercial application of the Bell inequality, I would have laughed. But here you go. This is a way that you can prove that numbers are random and no one is tampering with them. And so that's very valuable in the cybersecurity world, of course. So, so just to very quickly review what some of the concepts are. So a qubit is, of course, short for a quantum bit. And this is really just a 2-state system. You can think of it as like a spin 1/2 particle. It may not literally be a spin 1/2 particle. There's a lot of different ways to achieve this. A lot of different technologies are being used. But the basic idea is that it's just a 2-state system. And this is a more general description of the bit, which can only be a 1 or a 0. Here it can be both. And entanglement is that these qubits, their values may not be independent. We say that they're correlated. So the value of one depends on another. And this is a purely quantum effect. There's no classical description of this. And so you actually need to talk about all of these qubits together for the full description. Superposition is, of course, just describing the ability for one to move, for one state to be in more than one state at once. And so this is really where the power of quantum computing comes from, that you can kind of describe 2 problems at once. And so this leads to a lot of speed up. And there's been talk about something called quantum supremacy or quantum advantage. And this is just when you have a quantum computer doing something faster than a classical computer. And it doesn't mean that everything is faster. Quantum computers tend to only be good at certain things, but it's just finding one example of something that a quantum computer can do better than a classical one. So why do we use them? So the point is that we want quantum computers to run faster than a classical computer, to do it in less operations. And so there's a lot of effort in making these quantum programs or quantum circuits as efficient as possible. And so just as one qubit can produce two answers, there's two possible superposition states, then 2 qubits has 4 possibilities and 3 qubits has 8 and so forth. By the time you get to 300 qubits, there's actually as much data in that as all the atoms in the universe. And so this means that even theoretically, you couldn't build a classical computer more complicated than that. So 300 qubits is as complex as the entire universe. And so that's really why people are so excited about quantum computing, because it could solve problems that we never could have even hoped to have solved using classical means. So they really do exist. This is just a small sampling of some of the bigger names in quantum computing. All of these images are real. These are real quantum processors. These are not artist illustrations. They're using a lot of different technologies, and different groups are using different strategies. Some are trying to increase the quality of the qubit. Some are trying to increase the number of qubits. There doesn't yet seem to be a clear winner, although that may have changed in the past day. So this is a chart that I usually show about the progress that's been made. Many of you are probably familiar with Moore's law, in which computational power doubles every 18 months or so. And IBM has kind of popularized this idea of a quantum volume. So it's one metric which encapsulates the number of qubits and the quality of qubits. So it's roughly the power of a quantum computer. And that has doubled every year. So this is even better than Moore's law. So it's every 12 months, not at 18. So IBM has had steady progress, doubling it every year. And the numbers I've plotted there are the quantum volume. Honeywell has come out with a lot of progress. So just recently they came out with, just 2 days ago actually, they came out with a 128 quantum volume processor. And this seemed wonderful. They claim that they can increase the power by a factor of 10 every year for the next 5 years. And we were very excited about this. But then apparently yesterday, IonQ came out with one which they claim has a quantum volume of 4 million. And I feel a bit like I'm bringing coals to Newcastle, because I know there's people on this call who know far more about this result than I do. So I won't go into detail, but this really is extraordinary if it's true. And I'm really looking forward to reading more details about this. This puts us about 6 years ahead of schedule from where we thought we were, even under the most optimistic circumstances. So this is really fantastic. I've been telling people that we were hoping a commercial benefit would be there in 2 to 3 years, but again, this may put us several years ahead of schedule. So what do you actually do with quantum computers? So these summarize kind of the main applications. So one of them is chemistry, and this was actually the very first application thought of for quantum computing. And there's a lot of interest from pharmaceutical companies and material science companies about what you could do with this. There's a lot of logistical type things that people are hoping to do. In IT, there's no shortage of using machine learning, of course, and this is especially true in the financial world. Of course, you want faster, more accurate, like trading algorithms and fraud detection algorithms and optimization algorithms and things like this. And these are all things that we think quantum computers would be very good at. So some of them have quadratic speedup and some have exponential speedup theoretically. And so there's a lot of work being done in seeing whether this translates into the real world. So I wanted to start by giving an example. So this is something called the Knapsack problem, and it's a classic problem in machine learning. And so the idea, it's very simple, that you're given some sort of container like a knapsack, and it has a finite capacity. And you're given a list of items, and each of them has some sort of weight and some sort of value. And so you're trying to maximize the value of what you can carry within this constraint, that everything together has to be no more than this capacity. And so this has been studied a lot classically, and there's good heuristic algorithms on how to solve it, but it's very difficult to solve exactly. And we've been developing a way to do this with a quantum computer. And so I'm showing this because this is very typical of how to solve machine learning problems with quantum computing. Even though there's a great speed up, there's a great increase in speed, the trade-off is that you're not necessarily going to get the correct answer. that things are still probabilistic. And so on the left here, this is a chart where we did the knapsack problem on IBM's 5-qubit computer. And so on the horizontal axis, those are all the different possible results from the 5 qubits. So when you measure the qubit, of course, you have to get a 1 or a 0. So those are all the permutations that you could get there. And we know what the correct answer is. On a 5-qubit problem, we know how to get the correct answer classically. So you see that the correct answer is most likely to be the one that we end up with, but it's not guaranteed to be the right answer. And then on the right-hand side, it's the same problem, but on IBM's 10-qubit simulator. And this had actually never been done before. No one had even attempted a 10-qubit simulation of this problem. And you see that, again, you're most likely to get the correct answer, but it's not guaranteed. And so we're actually working on this right now, looking to scale this up to more industrial scale type problems. So this is a great example of how machine learning works in quantum computing. There's probably a speed up, but the trade-off is that you're not guaranteed to get the right answer. Now, to talk a little bit more about chemistry, this was actually the very first problem realized for quantum computing. Feynman was looking at this, and he saw that the equations for molecular chemistry are very simple. We know what the Hamiltonian is. We've known for 100 years, but it's very complicated to solve it. You get all these complicated equations, which are all entangled, and it's only solvable in the very simplest cases. And so when I say solve, of course, I'm referring to calculating the wave function of the electron. It makes this cloud type shape, but has all these interactions going on because, of course, the electrons are attracted to the protons as well as repelled by each other. And so only in the very simplest cases can you solve that. In the complicated cases, which are the ones that are of most interest to us, that's where it would just quickly choke a classical computer. There's no way that we could do this using conventional means. And this is the interesting part. This is where pharmaceuticals and material science really become interesting. And this is one reason that pharmaceuticals take so long to develop drugs. It's expensive. You have to do it by trial and error. So it's expensive and it's kind of dangerous, and you have to do it in a lab, and the results aren't always very certain. It would be wonderful if it were more like an architecture problem where you just design on your computer kind of what the building looks like, and you can check its stability and the cost and how it looks, and you can do all these things long before you have to go onto a construction site. So ideally, we would like to do the same thing when designing medicine. We would like to understand a lot on the computer long before we ever go into a lab. Now, what would you do with this? About 2% of the world's energy supply goes into making fertilizer. And this is called the Haber process. This is a very inefficient process. We've made very little progress in 150 years, and we know that bacteria are much better at this than we are. We just don't know how they do it. And so if we could design a more energy efficient fertilizer process, that would be revolutionary because it would be cheaper and better for the environment and such. Another example would be designing more energy efficient batteries and solar panels. And then finally, personalized medicine. The way that we do medicine right now, it seems almost comical compared to a lot of other technologies. So as I said, drug companies have to do this basically by trial and error, and they can only design one medicine for a whole group of people. And for some of those people, the medicine may work. For some people, it may have no effect, and for some others, it may even be harmful. Ideally, you would like to design a drug for an individual based on their genetic makeup. And so you could design a drug just for them for that condition. There's no way you could ever hope to do this with a classical computer. And so the hope is that you could use a quantum computer to actually design the molecule. So you would give as input to the computer, here's the person's genetic makeup, here's the condition they have, and these are the side effects I want to minimize, and the computer would actually tell you what the molecular structure of the medicine is. And we're not there yet, of course, but the hope is that maybe in 20 years or so, this is something that we could be doing. So, so the way that we do this is using the way that we hope to be doing this is using our chemistry application, which we call UMAN. And this was actually the first commercial quantum chemistry application. So a lot of groups have different algorithms that they use for individual things, but UMAN is a full application that we use. And we've already been doing this with industrial partners. So how does it work? So you give it input. So right now you give it the molecule that you want to study. So you give it the molecular structure, And you input this to human, and human knows, so figures out what the molecular structure is, and then it figures out what the Hamiltonian is, and it will actually solve this. And so it specifies all the different quantum gates that need to be done to represent that configuration, and it hands it to our compiler. I'll talk a little bit more about that later. And the compiler works to make the circuit as efficient as possible. And then it either gives it to the hardware, if you happen to be running on a real machine, or to the simulator, if you're just simulating it. And so then it can read off results. And so these problems might be things like, what is the ground state of a molecule? What are the first few excited states? What is the sensitivity to photons? So different things like this, different chemical properties that you might want to specify. And so we've already done this. Again, I can send you articles after this. So it really does work, and it's becoming quite accurate. So the compiler. So tket is a compiler that we've developed ourselves. So what does that mean, and why would we want to do this? So just like with classical computing, a compiler is what sits between you as a programmer and the actual computer. So it takes the code that you're writing and it turns it into instructions that the quantum computer can do. And in quantum computing, we're sort of at a disadvantage right now. It's still very much the Wild West. There's a lot of different groups with different hardware platforms. There's a lot of different programming languages which run only on that particular platform. And what we've done is we've made a hardware agnostic compiler. So you can use any of these programs as you wish, and they all connect into tket, and tket takes the circuit that you've designed for your program, and it finds the most efficient way to execute it given the machine that you've chosen. And we've already included all of the popular ones that you're familiar with: Honeywell, Google, Rigetti, IBM, Microsoft. There's a group called Pascal in Europe that we've just started a collaboration with. And so if you change platforms, say you go from the Google machine to the IBM machine, you don't need to rewrite your code completely. And that would be the case if you originally wrote it in Circ for Google, you would need to completely rewrite it to use IBM's machine in Qiskit. And with tket, you don't need to do that. You literally just change one line to say that you're flipping from the Google to the IBM and nothing else. And tket will take care of everything for you. All the details of the hardware are built in on the back end. So we have these partnerships and we work closely with their engineers. So we understand all the details of their platform, so you don't need to. You can just focus on writing your program. Now, this is especially important nowadays because of this NISQ era that we're in. And you might have heard of this term NISQ. So this is noisy intermediate scale quantum. This means that we're sort of, we have quantum computers which work, but they're not at the scale where we could do error correction and things like that. So this puts us in the band of about 50 to 100 qubits. They have relatively high error rates, like 99.5% fidelity. So this means about 1 every 200 operations will go wrong. And this means we can't yet do error correction, although again, things may have changed in the past day. But when I wrote this talk last week, this is where we were. So this means you have to be very constrained in the size of the program that you write. You don't have that many qubits, and they have a large error rate. So if 1 in every 200 qubits gives the wrong answer, you can't really have more than about 200 operations without expecting something to go wrong. And so that's why people have focused a lot on hybrid algorithms, where you use a classical computer and a quantum computer, and you get the classical computer to do as much heavy lifting as possible, because we know those work and they're pretty fast already. And you let the quantum computer do the things that it's best at. So this would be like evaluating a quantum state and determining the energy levels or something. And so a lot of people have been developing these hybrid algorithms. You might have heard of a few, like the VQE or QAOA are a few examples. So how would you actually use tket? So it's actually very simple. You can download it from GitHub, and you just use pip install, and you're ready to go. So it's just a library that sits on top of Python or C++. So you would write your program in Python or C++, and you would just call in different commands, which are instructions for the quantum computer, whichever one you're using. And so that's how you would use it at a logistical level. So the way that it works is it takes your circuit and it makes a pass, and it looks at all the gates and it looks for ways to simplify it. So if for example, if you have like to X gates in a row, it knows it can simplify that to just the unit operator. And so it has a lot of sophisticated things that it can look for to simplify things. I'm about to show you some benchmarks, but this has shown great improvement. So we did some internal benchmarking, but even Google has been using this for a lot of their own algorithms and such. The specific way that it does this is it takes the circuit that you've written. So on the upper left there, this would be a typical circuit that you would type in. These are the instructions to represent the circuit below it. And what tket does is it takes that circuit and it decomposes it into a bunch of graphs and arrows and such. And so it looks for mathematical simplifications that it can do using that. As I said, tket knows about what the architectures are. And these are 3 examples from IBM and Google and Rigetti. And this shows how vastly different the architectures are. And each of these qubits has its own error rate and its own coherence time and such. And you can tell, of course, at a glance that they have different couplings to other qubits. So all of these details, as well as what the basic gate operations are, these are all included in tket. So tket will automatically find the most efficient way to implement your program on that architecture. And so it will perform a mapping of your program to what the qubits are, and it knows how they're coupled and everything. So again, all of these things are taken care of for you. We've just released version 0.6, and some of the new features are support for Honeywell's new machine, as well as AWS bracket. And I see that the spelling check corrected bracket. I know there's no C there. So you can now use those platforms. We've improved support for QuizKit, which I think you know is IBM's framework. And we've added some extra features. You might have heard of ZX Calculus. So this is an important tool which actually Ross Duncan, who's head of our compiler group, he's actually one of the co-founders of. And so this is all built in to it. These are some of the benchmarks that we had been doing. So we use 29 benchmarked circuits. And then the metric for success is how many two qubit gates are involved. And so we check this on a lot of different architectures, and you see that, so full pass, that's the name of tket's chemistry algorithm. So you see that's the green triangle, and you see that these are definitely on the bottom. So for a large phase space of different circuits, tket was significantly faster than other compilers. So we've had very good results with that. So it's free and available. If you just want to check it out and use it for personal use, you can go to the GitHub repo and download it right now. So I encourage you to do that. There are also academic licenses available. It's free. Just contact me first so we can sign you up. And so this includes a lot of support and training that we can offer you. We do also have commercial licenses, and I know in this audience that's probably not an issue, but we do offer licenses both for just internal research and development, and also if you wanted to deploy this commercially. But again, that's probably not applicable here. So how do you actually access a quantum computer? So you probably know that IBM has the Q experience. And so this allows you to log in and you can use their lower end machines, like the 5 and the 16 qubit machines. You can do that for free. But the disadvantage is, of course, you have to sit in the queue. There's a lot of people using their free machines, and so you may not get to use it very much, and you can only use the lower end machines. IBM has much higher end ones. Unfortunately, you actually have to have a 3-year commitment, and each year costs about $1 million. And so it's not great for testing. We are uniquely authorized to resell access. And so if you're interested, we could sell you, you can share the machine with 3 others. So you would have quarter share access for 6 months, and it's priced proportionally. And so this is well within the means of academic grants and such. So if you would like to use their higher end machines, we can certainly speak with you about that. And then Honeywell, as I mentioned, we're close with them, and so I can connect you with them if you would like to access their machines. So just by quick summary, there's enormous benefits coming to quantum computing. We have thought that there's quantum advantage in maybe 3 years, although that may be a little sooner than we thought. it takes time to develop these algorithms. Sometimes when I speak with people, like commercially, they seem to think that we'll just jump in once it's a little more mature. And I think what they don't realize is it takes time to understand and develop these things. And so it's actually great to be speaking to all of you, because you're all young and you're already interested in the field. And so it's great that you're getting into it. We expect enormous progress in the next few years. And so I would recommend you start now. In terms of what you can concretely do, so again, I would encourage you to download tket. If you want to use it just for private use to play around with, you can do that immediately for free with no issue. And we're happy to give you academic licenses. We're also happy to discuss giving you access to IBM or Honeywell's machine. And then a few of you might have overheard us talking in the beginning. We have internships, and this does include undergraduates. And we make decisions in December for next summer. So please reach out to me if you're interested in this, and I can connect you with our team. These are real projects. These are not Mickey Mouse things. These are real things. And so, so it would probably be a really good thing for you to do. One question was about any citizenship constraints on that. In the past, we've had people actually move to Cambridge for the summer to work on this with the team. That obviously required a UK work permit. That may not be an issue this summer. I think we'll just have to play it by ear, but please do get in touch. So I'm happy to answer any questions. I left plenty of time for that. So if any of you would like to chat about that, let me stop sharing here. Yeah, I'm happy to answer any questions that you have.
Yeah, so I guess we're a little ahead of schedule, so we have plenty of time for questions if anyone wants to ask.
I do have a question. So as a primarily a software company, how do you sort of keep in touch with what new things are coming out in academia and new big results that might change sort of the research direction? How do you deal with that?
Yeah, so some things we learn just like you do. We read about them in the news, and so we're constantly looking online for new news development. Sometimes we know ahead of time, like if a hardware partner is going to come out with something, we do know ahead of time, and so we can kind of like for tket, for example, we're given a heads up, and so we can start to integrate their new platform into ours, or sometimes we're asked to beta test new hardware. So for example, Honeywell, 6 months ago, I think, we were given access to their new machine. And so we've been running a lot of programs. And we give them a lot of feedback. We tell them how it works and such. And so it's a mix. Sometimes we just learn like everyone else does, and sometimes we know a little bit ahead.
Thanks.
Hi, thank you very much for the talk. I was wondering if you could talk a bit about Bob Cook's like QNLP work and what you see as some of the applications of that.
Sure. So natural language processing is when you're using machine learning to understand text as we use it. So understanding the structure and the meaning of sentences. So this would obviously be important for things like Alexa, where Alexa first has to understand what words you're saying and then what you mean by that. And unlike a programming language where humans have been trained to write their code in a way that computers can understand, now computers have to understand what we mean by this. And that's a lot more complicated because humans are not always so logical. And so Bob Cook, who's a professor at Oxford, he's been leading the quantum natural language processing effort. And I'm not on that scientific team, so I don't know the details of it, but I know that they've written several papers on it. And I believe a month or two ago, they came out with some results. They've actually been running programs and doing things. I think this kind of represented the first time people had done QNLP in practice. So Bob Cook, coincidentally, he was the advisor to Ross Duncan, who as I said, he's head of our tket group. He was also the advisor to Will Zhang, who some of you might know. He was head of algorithms at Rigetti and then just recently started the group at Goldman Sachs. So Bob Cook has already become kind of one of the godfathers in the quantum computing space.
So first of all, I would like to thank Catherine for allowing me to join this great community. Let me just tell all of you that I'm not a Duke University student. In fact, I live in Egypt, in the Middle East, or the Arabian region, and it is a great opportunity and a great pleasure for me to attend this with all of you. So in fact, I have plenty of questions, but in order to give space to others, let me ask for now only one. So Professor Mark, some skeptics claim that noisy intermediate scalable quantum computing term was made only for the commercial interest, but in fact, it has no applications so far. So is that true?
Yes and no. So I was actually in the audience when John Preskill announced this term at QTB about 3 years ago. Yeah, I think it was the first QTB in December of 2017. So yeah, so there's no formal definition of NISC. It's sort of a general category, which is a bit fuzzy. So I think Preskill was trying to make a little more concrete this idea that we do have quantum computers. They do run programs. They do things, but it's not at this point where, you know, it's 10,000 qubits with which work perfectly, and we can do error correction, and so we can think of them as these ideal universal machines. We are working hard to try to find practical things that can be done with them. For example, our chemistry work. So we've written this program, Human. We can identify the ground state for small-ish molecules, like a dozen electrons and such. It gets the right answer. We can figure out the excited states. In our work with JSR, Japanese synthetic rubber, they were looking at states which were highly entangled, and this is something that a lot of classical computers would have a lot of difficulty doing because they don't handle entanglement very well, whereas a quantum computer can handle it very well. And so we were purposely looking for examples where a quantum computer could do it and a classical computer couldn't. And that was true. So we actually were able to get the right answer pretty quickly compared to a classical computer. So we're not at the stage where quantum computers can do like amazing things yet, but it's starting to catch up to where classical computers are. I think it's just a nice way of kind of moderating expectations.
Hi, Mark. Thank you very much for your talk. I have a question about the quantum chemistry side, and in particular, your drug design. As far as I know, like the encoding methods that I've heard of, like Jordan Victor, require at least 1 qubit per atom. And I know that like clinically relevant peptides can be on the order of thousands or tens of thousands of atoms. So how long is it going to take for that to be available, or do you have a way to speed up or compress the representation, if you like?
Sure. And it's yeah, it's not just one qubit per atom. It's actually 1 per electron, or whatever your degrees of freedom are. And so so there's usually many electrons in an atom. Yes, it will take a while, and so that's why. Yeah, I was just starting to say, I think NISC is kind of a way of moderating expectations, because sometimes people in the business world, they kind of get carried away. They just see a headline with quantum computing and they think, oh, okay, let's do this next week. It will be a while before we can do large molecules for drug design. And so I don't want to trick anyone into thinking that that's on the schedule for this year or something like that. But we still hope that we can do interesting stuff with smaller molecules in the next few years. So yeah, it will be a while before we can do large molecules.
I see a question in the chat that asks about internships and how you can apply.
Yes, so just send me an email and I'm happy to connect you with our human resources who can give you more information. I don't know specifically what the application process is. I imagine they would just ask for your resume, and they would pass it to the scientific team. And if they're interested, they would ask to do a Zoom interview or something like that. So it's just a kind of a normal process. But yeah, please do contact me soon, because they make decisions around December.
Professor, are there remote internships where I could?
There weren't in the past, but This year, I think there may be. I think we'll have to play it by ear. I think nobody knows what's happening. So that may be a possibility this year.
So someone else asked, how does D-Wave's quantum computers fit into this whole frame?
Sure. So D-Wave was the first to claim they had a commercially available quantum computer. They did that quite some time ago, and it uses a different technology called quantum annealing or simulated annealing, and it's very different from what I've described up until now. So what I've described is called the gate model of quantum computing, where you have these qubits, and you can control each individual qubit. Some qubits are coupled to each other, and some aren't, but you can control each qubit individually, and then at the end, you measure the values of the qubits, and you get ones or zeros. With quantum annealing, you have a lot of qubits, like thousands or tens of thousands, and what happens is that you encode your problem in the couplings between the qubits, and the system then relaxes to the ground state, which will be different depending on what you've done with the couplings. So it can really only solve one particular problem. It's called QUBO, quantum unconstrained binary optimization. So it's one specific mathematical problem that you can solve on the D-Wave. And if that's the problem you want to solve, it's great. It does do it very quickly. It's controversial about whether that's actually a quantum computer, though. It seems like it actually might just be a very fast, specialized classical computer. It doesn't seem like there's anything quantum about it. So I want to make clear, it is a computer. It does solve something. It solves this one type of problem, but it's not clear that it's quantum. We don't support D-Wave because it's so different fundamentally, and so we haven't worked with D-Wave. Yeah, it's just too different.
I guess I have a question that I've been saving. So, as a physicist, why did you make the switch into quantum computing? And do you think there's any application for quantum computing in like very theoretical physics research?
Yeah. Why did I make the switch? So I was doing string theory, and I don't know how much you know about string theory. So it's beautiful mathematically, but no one has found any concrete proof that it's right. So this is actually what I was working on. I was trying to use cosmology to look for proof, like signatures of string theory in the CMB, the early radiation. So no one has found an answer either way. It gets frustrating after some time to be working on that and not know if it's right or not. I don't regret having worked on it. I loved it, but it can get frustrating. And so then about 4 or 5 years ago, when I was kind of rethinking what I would be doing, I started hearing about quantum computing, and it was like D-Wave I had heard about, and Google was building one, and this seemed amazing. The idea that you could actually build a computer to do all these things that I'd been doing kind of theoretically, like entanglement and superposition and stuff. Suddenly they were building machines that could actually do this, and it was useful for something, and you could solve problems, and there was probably a lot of money to be made in these things. And so it really seemed perfectly timed. I was looking to get into something, and it seemed like I could kind of get in on the ground floor. I was obviously born too late for the Silicon Valley revolution, but this seemed like such a perfect mix of using my physics background and some business experience, and I've always liked computers. And so I was really excited, but as I mentioned, I was frustrated. It was hard to get into the field, not knowing anyone and not having a background in it. What was the second question?
Do you think quantum computing has any applications in helping theoretical physics research?
With theoretical work, yes. Yes, so yes, I know of several things that it can help with. So first is I made that joke about I never would have thought that the Bell inequality would have had a commercial benefit, and it does, but it also means we can understand the theory behind things like superposition and entanglement much more, because every time you're sending commands to the quantum computer, you're actually doing a quantum experiment. And so it's really cool. We can design all sorts of funky things that previously would have taken millions of dollars in specialized equipment and such, and now you can simply write a few lines of code and send it to IBM's 50 qubit machine in upstate New York, and for free. And so I think this will revolutionize the way that we understand quantum physics. You can write codes to check things. And you probably heard about quantum error correction. So this is a clever way of making it so that if something goes wrong with a qubit, the other qubits will compensate because you've spread out the information amongst several qubits. There's something called holographic quantum error correction. So you might have heard of the term holography, where there's evidence to suggest that the number of degrees of freedom in the universe isn't really 3 + 1. It's actually more like 2 + 1. That what we call 3 spatial dimensions is a clever distortion, and that you could encode all this information on a 2D surface. And so people have been working out theoretical maps between this holography, where the information is spread out in a clever way, and qubit error correction. And so, so hopefully they'll make this a little more concrete. But it does imply that we could be using quantum computing as a tool to understand fundamental science.
Thank
Hey,
you.
Mark. Thanks for the talk. Can you hear me?
Yeah.
I just turned on my mic.
Yeah.
As somebody who's about to graduate, hopefully graduate soon, I kind of wanted to follow up on Catherine's question and ask specifically, like, what, if you could just go into, like, what your decision was or your thought process and how you've liked it so far when you switched into business, the business side of stuff. And, like, did you have to get your MBA or anything or stuff like that?
No, I didn't go to any schooling. So it was in 2014. I left academia and I did my startup, and I just kind of assumed, well, physics is hard. I'm sure I'm smart enough to figure out the business world. And yeah, I was quickly shown otherwise. There's a lot to the business world that I wasn't aware of, and I'm really glad that I had that experience. And it certainly helped me here. Just running my own startup for 2 years has given me a lot of perspective. I didn't do any formal training. Even though my startup didn't work out, I kind of look at it like if I had gone to Harvard Business School or something, that would have been about 2 years and the same amount of money that I put into my startup. And I probably wouldn't have learned anything more. I found it really valuable just to be running my own business. And so, so I'm actually very happy that I did that.
Thanks.
So Professor Mark, could you tell us how
far away?
Okay.
Sorry, go ahead.
Go ahead, Jake. Go ahead, it's fine.
Hi, Jake.
Okay, I'll go. Sorry. How far would you say we are from a quantum programming language, where instead of coding gates or gate sequences, you come up with functions?
Yeah, so it may be a while. Just the nature of what's happening, you do have to have a pretty detailed knowledge of it. People have remarked it's sort of like back in the 60s when you had to know what like machine language was, and you had to be an engineer to be able to program it. And now even kids can learn how to program and stuff. That would be wonderful if it ended up like that. It may be a while before it's like that. Yeah, it's not going to be anytime soon. People have joked that they might use, that program developed by MIT for kids called Scratch. People have said maybe someone will develop like a quantum Scratch where you just fit the blocks together and it will run. So that would be wonderful, but I don't know if it will happen anytime soon.
So Professor Mark, could you tell us how can we overcome the multidisciplinary nature of quantum computing? I mean, in some cases, I try to pick up some quantum mechanics textbook, but it doesn't seem to catch up the spirit of computer scientists. So that seems to be somehow confusing.
So you're saying, as a computer scientist, how would you learn the physics behind it?
Yeah.
Yeah, so I would understand linear algebra very well, because that's really what it is. I know the physics terminology can be intimidating, but it's really just linear algebra. And so if you just realize, it's a complex valued two-state system with unity norm. Yeah, it's really just fancy linear algebra that you're doing. And so I would suggest that. That's a really good idea, though. Someone should write a book like Physics for Computer Scientists with an eye towards quantum computing. So maybe one of you can write that book.
Oh, I just want to say that we're offering a house course next semester at Duke for people who are interested in quantum computing who don't have much background in how to code, and we're going to be using Qiskit. So this is an applied approach to quantum computing. We'll be building some simple quantum algorithms and things like that. So if you're interested, definitely be on the lookout for that. But just a side note, keep on asking questions.
Could you talk about how you've been using the Bell inequality? That sounds really interesting.
Oh, sure thing. So yeah, in cybersecurity, you need random numbers. So anytime you do keys and stuff, you want to use numbers that no one, especially your adversary, could have predicted. And a lot of people don't understand that it's hard to come up with a random number. They think, oh, I could roll a die. But of course, when you roll a die, you're using classical physics to do that. And so in principle, you could predict how the die will land. Usually you just don't want to bother doing that. And then people say, well, I could ask a computer for a random number, but a classical computer can't do anything random. It just follows instructions. It's completely deterministic. And so what classical computers do is they have a pseudo-random number generator, which just uses internal settings in a complicated way to make numbers which superficially look random, but they're not. And there have been examples where people anticipated what the numbers were going to be based on clock cycles or something. In quantum physics, of course, you can have truly random numbers, and people have known this for a long time. And the past 20 years or so, people have built what are called quantum random number generators. And so these usually use technologies like tunneling or silvered mirrors or something to generate random numbers. And in principle, that might be okay. But the problem is that you have no way of knowing if these numbers are random or if they're being tampered with or if someone isn't, like an adversary is aware of these numbers or something. So anytime you use tunneling or things like that, you have no way of knowing, of checking what the answers are. In order to prove that these numbers are non-deterministic, you have to use the Bell inequality. And so what this was this Irish physicist, John Bell, he was thinking about trying to prove whether nature was deterministic or not, because people had speculated maybe there were hidden variables, and that's why quantum physics looked random to us, but maybe at a fundamental level, if you knew what these hidden variables were, you could predict how things would end up. And so he came up with a test, now called the Bell test, in which you measured things and you studied which variables commuted and which didn't. And he proved that it actually is random, that nature doesn't have these hidden variables, that it really is non-deterministic. And so what you can do is you can do experiments, and based on the statistics of those experiments, you can check whether there's correlations which cannot be explained classically. So that's called the Bell inequality. So you do an experiment many, many times, and you look at the correlations between different degrees of freedom that you're measuring. And so in the application of cybersecurity, what we do is we've built this device, we call it Iron Bridge, where it's measuring, so it produces a pair of photons, right? And they're entangled. So whatever state one photon is in, the other photon is in, and then they're both measured. As long as the entanglement is there, they should both give the same answer. So we don't know what the polarization is, but whatever it is, they should have the same polarization. If someone, so they're both measured individually, and as long as it's the same answer, then the machine outputs a 1 or a 0, depending on if it's horizontal or vertical polarization. So it's a random number generator in that sense. If someone tries to tamper or eavesdrop, it will break the entanglement of the photons. So the measurements will not always give the same answer. So they'll give the right answer 75% of the time, but not 25% of the time. So that's how the statistics will work out. So if the machine sees this happening, so it can quickly do like 1 million trials, and if about 1/4 of those trials are failing, if they're different answers about 1/4 of the time, the machine stops and alerts you and it says, whoa, something is wrong. Someone is tampering with me. And so that's how we can use the Bell inequality. It actually checks the statistics of how correlated the photon polarizations are. So, so that's how we use it.
That sounds good. So we have probably time for one more question, if not.
Sure.
Yeah, I think I have the perfect last question we could end up this meeting.
Okay.
So, Professor Mark, what, from your own point of view, what is the best entry for an undergrad, or what are some accessible research problems by which
Sure.
an undergrad could delve into the deep of quantum computing?
Sure. I didn't do it myself, of course, but so first I see all sorts of videos and tutorials online. I see people doing that. I would follow, there's a lot of people on Twitter and social media and stuff who do a lot of outreach, like Anastasia Marchenkova. I know, so she's at Leximo in Berkeley. So she's been making some great videos, for example. IBM has a great educational program. They have these ambassadors, they call them, to do outreach. And so Catherine mentioned you're already doing work with QuizKit. And so I would encourage you to do that. I'd encourage you to try to get internships, or just email different quantum groups and ask if there's anything interesting that you can work on with them. They need smart young people. So don't think that you're annoying them. They need you. They will need to be hiring. So when I joined 3 years ago, there were about 8 quantum startups. There's now over 300. So there's going to be a lot of demand for this. So they want to meet you as much as you want to meet them. So yeah, so I would encourage you to kind of learn what the different groups are doing and then reach out. So thank you, everyone. I hope this was useful. Feel free to email me. Catherine can give you my email address and put you in touch. And so I hope to be visiting Duke in the spring. I would love to come back to campus and I can give maybe a more personal talk about what I've been up to for 21 years. And hopefully I'll meet some of you then.
Thank you so much, Dr. Jackson. And thank you everyone for coming to this talk, and have a nice rest of your day.
Thanks for the talk.
Thank you.
Thank you.
Thanks, Mark. Thank you.